Hello, this is Mr. Best. Welcome to Continuity and In Behavior of Rational Functions. We're going to identify the in behavior and the continuity of our rational functions today. We've done this before with polynomials, so you'll get a little refresh on that as well. First thing, what is continuity, or what is, when a function is continuous, what does that mean? At any point, if it is defined at the point and it passes through the point, then the function is continuous. It is discontinuous if there is a break at the point. So anytime there's a break that occurs in the graph, then it's going to be discontinuous. That could be, a point, it could be a vertical asymptote, or what we're going to look at, the third one is a jump discontinuity. So there's three types of discontinuity that I'd like to talk about. First one is a point discontinuity. So you could have something like, see here, we'll do a line, but then there's a break. Well, I'm going to have to fix this. What we'll do is create a little break there, and then we have a working here. Alright, we have a hole in the graph, or a point of discontinuity. So when does that happen? Well, in the last section we talked about where these holes in the graph occur. So these holes in the graph occur when you have factors that cancel. So when you have factors that cancel, you'll have a hole in the graph. Okay, so that's point discontinuity. We also have infinite discontinuity, and that can occur. Let me fix my line here. When you have an asymptote, could be vertical, horizontal, but there's definitely a break in the graph, and so we could have something like this. And where we have that asymptote is where we have a infinite discontinuity, because it shoots off to infinity. So this occurs when you have asymptotes. And then a jump, a lot of times this happens with a piecewise function. You might have something like this. Where you have a break in the graph and there's a disconnect there. So that's jump, and once again, a lot of times this happens with a piecewise function. Okay, also we did a greatest integer function as well when we had the step function. That was another jump discontinuity. So three types of discontinuity. Once again, point discontinuity, infinite discontinuity, and jump discontinuity. And you'll need to know all three of those and when, how to identify each of them. So let's look at a couple graphs here, and we're going to determine the continuity of each of the following functions. So I have the first one is a piecewise function, so this gets you some practice on piecewise functions. So if you want to pause it and try this on your own, at least to graph it as a review, that's not a bad idea. So at x equals -1, alright, that's, we're going to graph to the left. And then we're going to graph from -1 to 2, and then from 2 to infinity, and then I'll get rid of those at the end. So x squared, so we want to graph values of -1, so your input is -1, and your output is 1. So at -1, 1, it's an open circle because it's not included, or it's not equal to -1. So at x equals -1, the output's 1, and then you can do, -2 squared, which we know is going to be 4. So at -2, 4, you have a point, and then at -3, 9. So this will be part of your quadratic there. Alright, and then now we have the linear, but we're only going to go from -1 to 2. So -1, 0, 1, and 2, and this is for 3x plus 4. And so if you plug in -1, you get 1, you plug in 0, 4, 1, you get 7, and if you plug in 2, you get 10. So you're going to plot all of those. Now these are included, so you're going to have closed circles on each of these. So at -1, 1, it was open, but now it's going to be closed, so we'll fill that in. 0, 4, 1, 7, and 2, 10. We'll graph that. Okay, and then the last part is x cubed. So you'll graph values from 2 to infinity. Now these are going to go very quickly because you're cubing it. So 2 to the third is 8, 3 to the third is 27. So I'm already off the graph. So 3, it's not included, so it's an open circle at 8, and then this is going to shoot up very quickly. So what's the continuity? Well, it was continuous. As we work our way here, it filled it in, so it's still continuous. And then right there, we had a break in the graph. So at that point, it became discontinuous. And the reason is because of jump discontinuity. So this one is jump discontinuity. Okay. So we've graphed it and we determined the discontinuity on that function. Okay. Piecewise function can also be continuous, so don't just assume that it's going to be a jump discontinuity with piecewise. Let's go ahead and look at part B. We have g of x equals 3x squared plus 5x plus 2 over x plus 1. You know, we first want to go ahead and factor this one. So I'm going to use my guess and check method. I know it has to be 3x plus something and x plus something. Now factors of 2, it's 2 and 1, so I don't have very many options here. This would be, when I go to check this, this would be 3x and 2x, which gives me a middle term of 5x, which is what I wanted. So that looks like that works. Over x plus 1. And so we have factors cancel. Remember what it means when factors cancel. So we're going to have a hole in the graph at, or a point of discontinuity at -1 comma. Alright, where is that going to happen? Remember, you plug it back into, if you plug -1 back into the original, it's going to be undefined. So we plug it into the simplified version. And so when we plug it into the simplified version, that's 3 times -1 plus 2. So y would equal -1. So at -1, -1, you have a hole in the graph, and then the function that is graphed is just the 3x plus 2. So I can graph that. It has a slope of 3, so up 3 over 1, and that's the y-intercept. Up 3 over 1, and we'll just kind of continue this. A couple more points. Down 3 to the left 1. And so now, so we'll start here. And so it's a line with a hole in it. And so what kind of discontinuity is this? This would be point discontinuity. And there you go. Okay, so you can identify some of these things actually without ever graphing them, but just kind of practice graphing as well. Alright, on the next part, what we want to look at is I want you to do this without graphing. So without graphing, determine the continuity of the following functions. Go back to that first slide. Remember what happens. If factors cancel, you're going to have a point or a hole in the graph. If you have vertical asymptotes, you're going to have an infinite discontinuity, and if you have a piecewise function, a lot of times you're going to have a break in the graph like that. Possibly. You might have to check that one though. Alright, so maybe pause me, see if you can go through and identify the continuity on each of these. And I'm going to go ahead and get started. So the first one is a polynomial function. So a polynomial function on this one, we know with the leading coefficient test, it starts and ends like this. So there is no break in the graph, there is no domain restrictions. So for this one is continuous. Okay. On B, we want to check to see if anything cancels when we go to factor it. So if we factor the quadratic on top, we get x minus 6 times x minus 2 and x minus 2 on bottom. So that's right there where they cancel. We don't have to do anything else. Right there, we know there's going to be a hole in the graph. So this would be point discontinuity. For example C, once again, we want to factor to see if anything happens. We have x plus 4 and x plus 3. So not the same. So we're going to have two vertical asymptotes. We'll also have a horizontal asymptote. So this will be infinite discontinuity. And once again, that just means that the graph is shooting off to infinity. And then on D, remember what these brackets mean. This is your greatest integer function. So it's not a piecewise function, but it's a greatest integer function. And remember, this looks like this, where we have this step function. So that would be jump discontinuity. And that's just understanding the function, not actually graphing it or anything. Okay? So a lot of times we can identify what kind of continuity we have before we ever have to graph it or anything else. Alright, the last example, we're going to talk about in behavior. So when we do in behavior, we already have done this before with polynomials, is the value of f of x approaches as x approaches infinity and negative infinity. So I have my notation down here as x approaches negative infinity. What is the y approaching? As x approaches infinity, what is the y approaching? So that's what we're trying to answer. We're just going to now add rational functions to it. So for the first one I gave you, just as a review, this is a polynomial function with degree 3 and a leading coefficient that's positive. So remember, it's going to look something like this. So in terms of your in behavior, as x goes this way to negative infinity, y is going to negative infinity. Alright, as x goes this way to infinity, y is going to infinity. Okay, so that's really a review of your polynomial functions. Now when I throw in rational functions, what is it that we're looking at? You know, our rational functions don't behave like polynomial functions. They don't shoot off to infinity. You know, what happens to our rational functions? Think about this, you know, before I really answer the question for you. But, you know, think about this. What's going to happen when you have rational functions? Alright, you have vertical and horizontal asymptotes. You have graphs that look like this and like this. So what happens when x goes to infinity? Where is your y value approaching? And as x goes to negative infinity, where is your y value going? And hopefully, what you recognize is that these values are getting closer and closer to the horizontal asymptote. So if you can identify the horizontal asymptote of a rational function, then you can identify the in behavior. Okay? So I'm going to take this maybe. And we're going to answer these questions now looking at the horizontal asymptote. Alright, so on this one, on part B, you have degree that are both 3. So your horizontal asymptote is at 1/2. So as x gets really large, by definition of an asymptote, for the horizontal one, as x gets really large, y gets closer and closer and closer to 1/2. And so As x approaches negative infinity, it goes to 1/2, and as x approaches infinity, it goes to 1/2. All right. What about example C? Well, this doesn't have an x on top, but if it was there, it'd be x to the 0. So the degree on top is smaller than the degree on bottom. So what's your horizontal asymptote on this one? That's y equals 0. So once again, your end behavior then is 0. D is a polynomial function. It's not rational. You're not dividing by x. So once again, just getting the picture of what the shape is. This is a quadratic opening up. So what does that represent? Alright, well, as x goes to negative infinity, your function is both approaching infinity. It's both going up. So you've got to be able to identify, if it's rational or a polynomial function. Both of these, a and d, are not being divided by x's, so it's a polynomial function. On E, the degree, is smaller on top again, so therefore the horizontal asymptote approaches, the horizontal asymptote is y equals 0, which means the end behavior is also 0. And then on the last one, the degrees are the same, so you take the leading coefficients, which is 6/4, and your horizontal asymptote will be at y equals 3/2. Once again, the end behavior then will be at 3/2. Okay, so that is it for continuity and end behavior. Make sure you can identify the 3 types of discontinuity: point, infinite, and jump. We also have functions that are continuous. Be able to graph and identify discontinuity, be able to do it without graphing, and then also be able to identify end behavior of polynomial and rational functions now. And so that is it for today. You will have a worksheet on end behavior and continuity. Thanks.